This is All Things Ansys, a podcast from the technical support staff at PADT. Episode 71. We buzz the treetops of what Ansys 2020 R2 topological optimization and additive have to offer, and check in on Ansys-related news. Good afternoon, everybody. My name's Eric Miller, and I'm one of the owners at PADT and your host for these podcasts. It's a lazy Friday afternoon before a 3-day weekend, and I have to say, it's been wonderful. My email traffic, a lot of people took Friday off, so my email traffic was wonderfully low today, and I was able to get some long put off projects done. So yay for 3-day weekends, or the day before 3-day weekends. As we look at 4 more months of 2020, a lot of things have backed up through the years, and we got to get a lot done before the end of the year. But I, for one, will be happy to wake up in 2021. You'll see we've got a lot of events coming up because we did, like everybody else, we kept on waiting, hopefully, for a better way to do it. But we're going to go virtual. And so there's a lot going on in the fourth quarter, and I'll cover that near the end of the podcast. Things are going well here at PADT. We're growing and adding people, so do check out our website. I was kind of hoping those would be up now, but they'll be up probably in a week or two. We got some new jobs we're posting, so if you're interested or you know somebody that's interested in working for us, check those out. We also have some new people that started that started this month or are starting this month. Some new blood is always a good thing, and a new perspective is always welcome. And it's been great to have them, even though we're talking virtually, join the team and add some fresh perspective to things. We also kicked off some pretty cool simulation projects that I can't talk about because we don't have permission to, but they're so cool. They're nothing really technically complicated, but they're really cool applications. So we're going to try and get permission to share those with people because it's some fun stuff. And as one of the engineers that's working on one of the projects said to me is that, it's a CFD job. One of them is a CFD job. And it's like, this is not very difficult to do, but it's such a cool application. I'm really having fun with it. So maybe we can share that. Today, we're going to have a discussion with Doug Oatis. He's our lead engineer for structural and CFD on the tech support team. And he's all around, if you've listened to him on the podcast before or worked with him before, he's a sharp-witted and funny fellow, and always good to talk to him and always good to get a brain dump from him because he really takes, basically this is a new feature and relates it to what's useful and what it really means for users. So we had a wide-ranging chat earlier today about topological optimization and Ansys additive. And one of the things that really came out of it, as you'll see, is that it really established these two tools as now really fully functioning, capable tools, and that really add a lot of value. So let's learn from Doug. Welcome back to another discussion today about the Ansys additive suite. Specifically, we're going to talk today with Doug Oatis about the tools for topological optimization as well as simulating the whole additive process in Ansys. How are you doing today, Doug?
Pretty good. Smoke's kind of cleared up in Colorado, so it's just, we're staring at it's going to be like 90 through the weekend and then snow on Tuesday. And so I'm trying to
fall for you.
I am bracing myself for the 70 degrees swing that we're staring down.
Hopefully nothing will crack with that kind of a thermal change. Yeah. Oh, that's crazy.
Just our resolve.
Your resolve. That's right. 2020 is still got.
Right. It's par.
That's so crazy. Well, one of the more popular topics here on the podcast, as far as number of downloads and things, is when we talk about what we can do with these new optimization tools, as well as modeling, 3D printing.
I assume it's not because of me. I assume it's because of the actual what the software does.
Yeah, it's the software. Yeah, it could be you. I mean, it could be your fan base. Could be you're paying in other countries to log in and click. I don't know, but
how do you make money? Volume.
That's right. volume. So it's always a good topic, and of course we're going through about the 2020 R2. And so this is the area. Let's start with just kind of a very high overview for those that are new to it. What exactly are we talking about? What do these tools do we're talking about?
sorry, we're talking about topology optimization, right?
Yes. Mm-hmm.
Okay. Just because there's a lot of parts of additive manufacturing.
Yes.
And so on the printing side, Ansys is typically more focused on the metal printing process. But we'll start with topology optimization, which is really kind of process independent. And so topology optimization is essentially telling the solver to change or to remove material traditionally. So we take a model, we specify some constraints, like we want to minimize compliance. We want to, make sure stress maintains a certain value, deflection, anything like that. And then depending on the algorithm you use, we either turn elements on or off. We figure out kind of some closed loop topology shapes. Or starting with the last rev and now improved at this rev is we actually distort the mesh. And so topology optimization is typically you have two fundamental solvers or two available solvers in the mechanical environment. And so that's the historical, you'll see it called a SIMP method. It's a density method where you essentially go through and basically turn elements on or off. You track what happens when you turn those elements on or off, and then you keep repeating that process. And there's algorithms behind the scenes that do a better job than I'm explaining it. So you finally get something that matches your criteria. The other method is a level set method, which I am not smart enough to remember what a level set method is. It's essentially a different way of kind of creating closed loop topologies based off of your criteria. And so those are the two kind of, you start with a model and then we're essentially whittling away material. And depending on how you whittle away, that's either turning elements on or off, or you're kind of doing this level set method to form your own topologies. And then the other one is you'll see it called like a parameter free, or it's a mesh morphing, where you start with a shape and then the solver is allowed to distort that. And so one of the complaints or questions that we get is, how do I get a topology optimization to make something outside of my original shape?
Right.
And the answer is you make a bigger shape.
Right.
So the topology optimization, you can, if I know where my loads are being applied, I know where it has to be reacted out. I don't know what it needs to look like. Just make however big of a box, we'll whittle it down based off of your criteria, and that's your answer. Whereas the mesh morphing essentially stretches, distorts the mesh, and kind of comes up with your final shape. And so kind of the big thing at this rev is you can mix and match, level set, SIMP, or the mesh morphing.
Nice.
So all you need to do is apply, you can have one body that's allowed to distort. You can have one body that's goes through and uses the SIMP method. You have another one that goes through and uses the, what was the last one? Level set.
Yeah.
got lost in there. So it's pretty cool. And so, each one of these guys kind of has its own strengths and weaknesses, and really depending on what you're looking for. So, I think, we were talking before, I think there's, this release doesn't feel like there's a lot of cows, like Shazam.
Right.
It's a lot of kind of more consistent behavior, more consistent manufacturing constraints are being allowed, cyclic symmetry, and just kind of cleaning up how everything kind of behaves. And then in the next rev, I think there's some really cool stuff that will come out that kind of blends, not just a discrete algorithm operating on a single body, but kind of like a combination where you could actually whittle away material and then kind of tweak the mesh, that kind of stuff. But it's a lot of kind of cool things that you can kind of see are coming. It's like the foreshadowing of the next rev. I think is going to have a lot of really cool things there. Not to say that this isn't cool. It's a lot of just we can finally use moments of inertia, center of gravity for the density basement. And we can finally have a manufacturing constraint on the mesh morphing method, and that kind of stuff, and kind of the expansion of like a user-defined. It's called a user-defined function. That has a different connotation in my mind.
Right.
Like I feel like it's Fortran, so I'm instantly confused by it. But it's really just a way for you to tag, certain criteria like reaction forces, or basically say I'm looking at the relative deflection between two nodes, that kind of thing. And so, kind of all of that stuff. And like the last thing that kind of is interesting is behind the scenes, when you solve something, it's actually, and we're iterating on turning elements on and off, we're solving the model again. And, depending on how many cores you're giving it, one of the issues was we would solve the model. If you're solving on, 10 cores, you have 10 result files behind the scenes. The APDL engine combines all those together. And then we track, what happened against my objectives, my criteria, that kind of stuff. And then you go through and iterate onto the next one. So now it actually doesn't have to combine those distributed files. It actually reads the distributed result files. And so you can get some pretty good speed ups, depending on, how much disk IO, how many processors were used. So that's kind of a pretty cool thing.
It just seems like kind of overall they've filled in the gaps between capabilities and needs to make it more practical. Yeah.
Right. And I mean, you can kind of see that even with like this SIMP method, there's an advanced filter. So after you're done solving, you essentially have this map of elements that are turned on or off. And depending on, I think it's a linear filter right now. So it kind of looks a little noisy or kind of bland, actually. That's one of the things like the SIP method looks like, okay, I'm going to have to do a little bit of work to this in order to get it to work. The level set always has like these really elegant kind of like clean looking structures. Right. But if you put a nonlinear filter that essentially looks at, which elements are turned on and off, you actually start to turn a SIMP output of the STL. Behind the scenes, it's solving the exact same way, but the output STL starts to look a bit more elegant, a bit more kind of like, I don't know, like fancy. I don't know the right word for it. Like,
kind of almost more organic looking for me.
Yeah. So, it just kind of gives you some more, novel, maybe that's the word I'm looking for, novel shapes out of it.
Yeah, that's really cool. So it's, I mean, we've been advocating people should be using it for quite some time. It's been a useful tool, but it really seems like it's getting closer and closer to where, when we first started recommending it to people, it was kind of like, well, this will give you some ideas on what the shape could be. Where you might remove material, where you might add material. Now it's getting you much closer to that optimized shape.
Yeah. And I mean, and a lot of that is, the ability, when it was first introduced, you could do structural, maybe modal.
Exactly.
And so the ability to kind of, add these additional criteria to, and add additional manufacturing constraints. So that way you don't have to apply as much engineering knowledge or tribal knowledge to your part. So, you go through, you run a simulation, see where it took material out, then go back there like, well, obviously this won't work. This, because I have this manufacturing process. I have, all these different kind of what ifs that you'd have to essentially add back in. You can add all those up front, and the output shape includes those. And so, it's a pretty nice kind of, less work on the kind of creating that final shape.
And then that final shape comes out in something you can use with Space Claim. Is that still correct?
Yeah. Well, I mean, there's two ways that you can go through it. So there's you can go through a validation step that essentially takes that STL and shoves it into a downstream mechanical session. It automatically tags all your boundary conditions that you had, so that way you can easily reapply them. The only trick with that is you have to make sure that you use the the patch independent test measure. Yes. So that's not using, I think it might run something in Space Claim behind the scenes to kind of convert it from an STL to something else. But really, you don't have to interact with the geometry. The other way that you can do it is you can, when you right mouse click to create a validation system, you can specify, I want to go to geometry, I just want to go to mesh, and it branches off differently. So if it goes to geometry, now you go take that STL, go into space claim, and then you have the whole suite of reverse engineering tools. And one of the things there is like an auto skin functionality. So trying to, you can always create the geometry using, all these different kind of surface skinning operations, but it's kind of a manual process and very experience. Like you had to have done it before to be really efficient at it. In my opinion, it was one that never quite grasped. And this new one, essentially, you create a box, it goes through and does its thing, and seems to do a pretty good job.
Yeah, I think that's always been one of the more daunting tasks as you get done, and now you got to get in there and make something that in the CAD tool or something. And because it's in space claim, and because it's getting closer, and because they've got tools like the auto skin, it's just getting a much better process to get to that geometry you're going to work with. Cool. If users want some little advice here, so if somebody's interested in trying this out, you've been playing with these tools for a while now, a couple of releases now. What's your suggestion on how to get started? Are there good tutorials? Should they just pick a simple bracket and start there? What's a good place?
Yeah, I mean, the flat plate with a hole in it, or just a box with like imprinted things, and just play around with it. It's unless you start kind of stacking a lot of constraints. So, I mean, you can kind of think of it as the more constraints you give it, the more kind of narrow of a window you have of like a correct solution. And I mean, it's an iterative solution. And so, sometimes it can take a while to kind of find that valley that satisfies all of those constraints. I usually just start with like a really simple part. YouTube, you can go on YouTube and see all sorts of different videos from Ansys or anyone else of, running these different things. But I always just start really basic. If people are running them, my kind of past history is the SIP method is a bit faster. I think it's just been around longer.
Right. Yeah, it's got more in it. Yeah.
Kind of got that dialed in. The level set can take longer. It seems to be a little more sensitive in terms of being over constrained, but it's one of these where like all FEA, it should be a crawl, walk, run. Like first make because sometimes like all the constraints that you apply on something, like that shape doesn't exist. Like it's a legit thing that happens where you're just asking for unobtainium in like a weird shape that nothing will ever work. So start slow and add those constraints and kind of ease your way into it. And just realize it supports thermal loads, supports inertial loads. That might not be for the mesh morphing. I'd have to double check on. I forget what that supports.
But definitely for the other two, yeah.
Yeah. So I mean, it supports thermal, structural, modal. So those are kind of the three kind of big ones. And especially with modal, it can sometimes get tricky if your modes switch. So if, mode 3 becomes mode 2 kind of thing.
Right.
So, I mean, it's, take, I'd rather, spend, a little bit of time running some, like validation models rather than trying to figure out what actually happened in something that didn't work. So it's like all things FEA, start out pretty basic and just get more elegant after that.
Yeah, you can definitely bite off more than you can chew. And I know I've seen people do benchmarks or evaluations of topological optimization tools, and they start with this like complicated real world problem with all these crazy loads and everything. And that's not necessarily the best place to start. And it's just solve that flat plate with a hole in it or whatever it is first and see what it looks like and get in there and play around. And I don't know, is there anything else that you think people should know that's new coming out in this latest release, or anything else you want to share before you wrap it up?
Well, this is just the top opt, right?
Yeah, just top opt.
Okay,
yeah.
right. I think so. There was a nice way for lattice optimization.
Yes.
That's where you can essentially have an infill. So there's no reason a part needs to be solid.
Right.
So this is different, where you essentially are hollowing out and replacing something with like a honeycomb, or the honeycomb isn't the right word, but kind of just hollowing
whatever
out
that lattice is. Yeah.
And so there's a list of different lattice shapes, and pretty much what we're doing behind the scenes is solving for like a variable thickness or a density map.
Mm-hmm.
And so it's really cool. It is just really difficult to validate that performance, because historically you'd have to, you take your density map that you get from the lattice optimization, and then you'd run it into SpaceClaim, and SpaceClaim already knows the lattice type that you picked, which faces are kept or removed or stuff like that, and it creates this STL with a variable thickness lattice infill. The problem was always, if I want to do an optimization, I have to like actually mesh this, and
right, just crazy. Yeah,
it crazy kind of hard to do. And so there's a different way to kind of validate it, is rather than looking at it from a micro level where we're explicitly modeling all this stuff. Instead, we're kind of taking how printed circuit boards are modeled, where it's not necessarily I'm explicitly modeling little details. I'm providing a map of knockdown factors. Right. It's also similar to how the additive simulation tools simulate, support structures. It's not explicitly modeling all of the little support structures. It's essentially calculating knockdown factors based off of essentially an overlay. Right. And so the lattice optimization, you can do kind of a macro level validation. Obviously, you're not going to capture stresses and strains in the lattice members, but you can at least capture the actual deformation or kind of far field effects of the study. So that's kind of a nice other way to go about it.
Yeah, I think that's really powerful and allows us to really think outside of the box. I was just on a call earlier today with one of the 3D printing metal 3D printer manufacturers about how we can do these crazy lattice structures now, and it's pretty powerful stuff and big weight savings there. So definitely check that out. So it's not just moving the surfaces around; it's creating these variable density lattices. Can do some pretty cool stuff. So let's change gears. So we've done this. We've run these things and we've got geometry, or we've used traditional methods to get geometry, and we want to improve the build process. So what's new on the additive side of modeling that metal?
So additive, we now have we've always had all these different tools. And so we'll start, I always like to start first with additive prep because I think, this is the tool that lives within SpaceClaim. You feed it an STL of a part that you want to print. You specify, your build zone. You can now specify don't build here zones, like do not fly zones. If you have mounting hardware for your build plate or anything like that, so that way you can kind of play around with positioning all of your parts that you want to print on this. And what some nice things here is the additive prep allows you. It's a rules based kind of solver, not actually solving like an FEA or thermal, right? But it's essentially looking at the amount of support structure you need versus the build time versus the tendency to distort out of plane. And so kind of gives you this map on how you should orient your part in order to, you can think of those three as, those three are like the points on the triangle that you can set to optimize off of. And it'll tell you this should be the orientation you should use. Now, it's not solving anything, but it at least tells you, this looks like a good optimization based off of all of these rules.
Great.
Then from there, you can actually start and build your own support files. So you can identify surfaces that have whatever overhang you want. You can specify a lot of different support structures on these regions. You can add faces, remove faces. And so, I mean, a lot of times, support structures, it's easy to identify the overhang where it needs like actual support, but also supports provide, the thermal cooling a conduit for it. So, you can go through and add all of this stuff kind of ahead of time, and really nice kind of like pretty straightforward way to support your structure. So now you have your STL of your part, you have the STL of your support structure, and kind of new in additive prep is some EOS integration.
Oh, cool.
So EOS has been kind of the is it the industry leader? I think
they definitely the most machines out there. Definitely the most.
So I think I've lost all credibility now. It's like,
well, no, it's what. But how do you want to describe it? Because there are those that'll say their machines are the leading machine.
Right.
Sold as many.
They are the most common machines that I run into.
There we go. Yes,
maybe
definitely.
that's the better way to do it. So you can actually spit out like the CLI file and actually, go straight from this additive prep tool and go and generate a build file. So,
nice.
In addition to that, it's in space claim. So it's exposing some of these features to scripting. So if you, need to automate or kind of standardize a workflow, pretty easy to do that.
Very cool.
If you know the language, you can log it and then go through and see how it does it, and then go back and modify it. But scripting is available.
That's a really major breakthrough, because I think sometimes, especially on the manufacturing side, people are like, "Oh, it's just easier if I do it myself," in the real world. But if we can script it, we can really speed it up and make it more practical, and get the design team working with the manufacturing team to model, to make better parts and get fewer crashes and less distortion. So it's pretty cool stuff. Any features on modeling the actual build process itself that are new in this release, or?
Well, I mean, so we can close out additive prep and move on to the build process. That might be a good segue. I'll have to tip you later for that transition. I mean, you can think of additive prep as, I can go through, I can orient, I can create build support structures. I'm sorry. You can play around with, different, look at different, like kind of layer by layer scanned data and stuff like that. And so now you have an STL of your part, STL of your support, and you're ready to print. But before you actually print it, because that's not a cheap process, there's different ways that we can simulate the print process. And so there's 3 tools now that do this, kind of do this. So you have additive prep, print, and additive science. So those are the non-workbench, non-mechanical based utilities where it kind of almost feels like it's sitting in a web browser. You feed it an STL, you specify some machine parameters, and then there's multiple on the additive print side that's really intended to looking at blade crash, looking at some residual stresses, strains, that kind of stuff. So additive print now can there's 3 flavors of simulation. You can do a very quick oh my God, like an instantaneous, oh my God, I'm blanking on the name of it.
Yeah, I can't remember it either. Yeah, it's really fast.
It's a quick upfront. It doesn't pay attention to any like scan directions or anything like that, or directionality. The next step up is an orthotropic strain. Why doesn't this sound right in my head? This is horrible. Anyways, then the last one, the most detailed, is we can actually run like a full thermal history where we're using the build file. So just like we can write out the CLI for an EOS machine, we can actually read in an EOS build file and use those scan patterns, the scan directions, and stuff like that to fully understand the full thermal history, the full time history of the stresses that develop as you build up your part. And so, this is intended as, I have someone that is running a machine and they want to make sure that, this is kind of like a good first pass on making sure that the additive prep didn't miss something, because it is a rules based. So, you have all this stuff. And then the other thing you can do is, I can run my my print simulation to capture the stresses and strains that develop and stay and the distortion that happens. And then I can also now transfer my additive print simulation to mechanical APDL, and I can do kind of a progressive cutoff operation. So previously it was basically like poof magic, all of your support.
It's gone. Poof. Yeah.
It wasn't that easy. And so now you can do a progressive cut in by transferring this over to mechanical, which uses the APDL solver. So those are kind of the, and behind the scenes, APDL now supports writing out a result file for additive print to use. So it uses a VTK file format. And so you can run this cutoff procedure and then have additive print run a distortion compensation off of that. So we go through and we've, try to give, guidelines on, this is what the part should look like. This is what it actually looks like after you print it, after you cut it off. And so you can distort that input STL. So that way you distort into the correction.
That's the thing that I like the most. Because when we've used it in actual projects, that's been the most useful thing, is to be able to calculate that distortion and compensate for it and get the geometry you need.
Yeah, and I mean, that process is a little iterative. It's one of these where you kind of supply a few different compensation factors, and then you kind of do a secondary run through those just to verify. And so, I just wanted to put that out just because I don't want to, nothing is magic. Everything, it does require a secondary loop through it, but it is a really good way. And it's one of the bigger selling points for additive print is you can make sure that the machine that you have, because you can apply some calibration factors to your material models to simulate your build machine in additive print. And so that way, that, you can distort it. So on your machine, it prints and meets print. Yeah.
Your requirements at the end. Yeah, I agree with that. I just think it's come such a long way from the initial tool set and so much more practical. It's still a process. One of the things we always recommend is, the manufacturing engineers that are running the machines may not have the simulation background. So those of you who are listening that are on the simulation side that are interested in this, reach out to your 3D printing folks and say, I want to work with you on this. Let me use my expertise. I know how to run mechanical. I know how to I know these tools. I know the language. Let me help you model this process rather than you learning how to become a simulation person while you're doing everything else you're supposed to be doing as a manufacturing engineer. That's been really successful when people have done that. So highly recommend it. Anything else exciting you want to share?
Well, I mean, I can pivot to the additive science side.
Let's take a look at that one. To me, that's the up and coming. A lot of promise there. Where is it at today?
Yeah, so I mean, additive print again. That's for the person running the machine, making sure that what we print survives the process, doesn't break the machine, and meets the dimensional specs that we have. So, additive science allows me to play around with the build parameters. So, you can play around with, the laser wattage, the beam diameter, the scan speeds, all of the different kind of inputs that you can have. And what we're doing is trying to predict what does it actually do to the material. So, from a microstructure standpoint, from a porosity standpoint, those kinds of things. And so it's not all you're trying to do is essentially find that sweet spot for operating the machine that gives you, the correct printed material properties. I don't know, that's probably not the right way to say it, but basically making sure that, because as you tweak it and, the actual material performance and what you get out of it changes.
Right. Yeah. The material properties, the microstructure is different. And I think people don't realize how significant of an issue voids in the build can be, because the crack initiation sites, right? So you need to know if you get those parameters tuned in so you can minimize those voids. Yeah.
Yeah. So, within this tool, it runs on the same kind of web-based interface as Additive Print.
Right.
So there was another material that's added as a beta for the microstructure calculation. So that was 316L.
Oh, nice. Yeah.
I forget
Great
what the others. I think there's three others in there. So you have a list of 4 kind of out of the box, validated materials that you can use to see, what kind of microstructure and material characteristics you'll get out of it. They've also expanded kind of the machine parameters. So there were actually like limits to the laser beam diameter, or
okay.
Some of these, like, just kind of widening the range of available input parameters. And then the last one, it's an extension, meaning you're not going to see it out of the box. You have to contact your support provider and get access to download it. But it's a way to actually tune your own materials. And so, it's kind of been I don't want to say the limiting factor, but it's one of these like, well, we have all these materials already in there, but what if I have my own?
Right.
And so this is now kind of that. The beginnings of kind of implementing your own material models. And so it's not just as simple as, providing thermal conductivity and, Young's modulus and stuff like that. Like there's a lot of, kind of thermodynamic behaviors, absorptivity as a powder and as a solid, and all this stuff that goes into it. And so it's a way to essentially kind of tune your parameters based off of some test data that you have. And so pretty cool
that's
extension.
Very cool. That's a big step forward. Yeah. Because that's the thing we always run into as well. I don't run that material. I need
If I'm not running those 4 materials, then what do I do?
Exactly. Well, cool. I'm a huge fan of what the additive science can do when it's done. And I think it's really becoming a much more mature tool, and it seems like it's time to really take it. If you're in that space, and you need to understand what are the characteristics of the part when it comes out, not just the geometry, how much does it distort, really. It really looks like it's becoming mature enough to start digging into that. That's really cool. Very good. Wow, it makes me want to go. Oh, you got one more? What's the last one?
We have 2 different ways that you can simulate the print process. And so we talked about additive print. Right. There's also the Workbench additive suite.
Yes.
So Workbench additive, runs a well, this isn't a true statement anymore, but I was going to say it runs a transient thermal and then runs a static structural that pulls the thermal history. But that's not the case anymore. There was a beta feature, I believe, in the last rev that allows you to essentially run an instantaneous. That doesn't sound right. Oh, that's going to bug me. But it essentially mirrors the same solver functionality of additive print. And so, there's different, the Workbench additive is really more intended for, I'm a designer or I'm a designer and analyst, and I have a printed part. And before I hand this off to someone who's actually going to print it, I wanted to see, do I need to add a heat treat? Will it survive the print process? There's been blade crash that's been added to it. So you get this kind of cross-pollination between additive print functionalities and solver capabilities within mechanical. And so kind of continue along that cross-pollination. So for some reason, I'm on like a bees kick. I don't know.
You are on a bee kick. Yeah.
So there's a voxel mesher. So that's the mesher that additive print uses. That is now available within Workbench additive. So it's an optional Cartesian body mesher. After that, there's been, I think it was the previous rev, you could have STL supports, or like a layered TET mesh, and you could essentially have, you would need contact between two different parts that you're trying to print because they were dissimilar meshes. So the voxel mesh is great because you get a conformal mesh between all of your supports, all of your actual printed parts. So great. Cool. You don't have to worry about contact, any type of that stuff. If you're using a layered TET mesher, you're using STL supports, what have you. In previous revs, you would have to use an APDL command snippet to connect the two together. So it was, I'm now forgetting the actual command, but it was a pretty basic setup. You just have to provide a name selection off of your two parts that you're trying to do, and it's essentially doing like the old like CEINTF command where it's just constraining to elements between your different parts. So you don't need a command snippet anymore for that. It's an actual like bonded contact within your within the connections branch. So just removing that kind of hard to parameterize APDL. And I'm using hard to parameterize air quotes because if you know what you're doing, it's not that hard. But it's if you don't want to know APDL, you don't have to. You can just use the bonded contact within this. Okay. And so some updates to the wizard that kind of walks you through the additive process. And then there's an extension for simulating. And again, this isn't included. You have to contact your support provider and give you access to it for marriaging steel. I'm probably mispronouncing that, but it's,
I know what you mean though. Yeah.
And I'm now blanking on my steel structure types, but it has a really low transition point between two of them. And you get this weird effect to where depending on the temperatures involved, you can actually get like some downward, as you print stuff up, like the example is like a cantilever beam. So any kind of standard additive powder, as you print up that cantilever, it's going to tend to kind of tilt upwards towards the recoat. But because of this marriaging steel's tendency to shift phases doesn't sound right. Sorry, I'm not doing well.
Yeah, but I know what you're talking about. It's a different like Martin aesthetic.
It'll actually tilt downward, and so it's kind of like this. It's a very interesting material behavior, and there's just an extension that's needed in order to properly characterize it and capture it.
Yeah, we're really, it's almost like I feel like I need to go back to my material science class because we're really getting into that stuff. And
I've joked with people, it's like I feel like you have to go through college twice, like once like just in like a 6-month period, so you kind of know what things mean, and then you go back to it after a couple of years in industry because it's like, why do I have to learn this? It's like, oh, that's exactly what that's used for. So
yeah. Definitely, for sure. It's getting to be I think next time we talk about this, I'm going to split it into optimization and additive because it's getting to being there's so many capabilities and they're adding so much so fast.
I think you could make the argument that the topology optimization is kind of process independent. In that it's useful for extrusions or additive manufacturing processes that are polymer or metal. So it's not necessarily a metal printed specific, but it definitely is the feeder to the powder bed fusion simulations.
Yeah, definitely. It's exciting stuff. I played with it a little bit R1 recently and on a simple part, and I found it very exciting to be able to see inside and understand the process a little bit better. And like I said, like I really like is compensate for the distortion with additive print. And I need to get my claws into additive science. That sounds. I may have to find my material science book though and remember these terms.
Yeah, it's definitely one where. It's always nice to have like a underlying like basic concept of what's being solved. And I always feel it's like, oh man, I really should have paid more attention in school. But
that was one of those, I'll never use this. Well, here we are talking about these different things that we had never really looked at before. So I'm excited about it. same thing, I think, as well. If you're interested in getting in using this tool, definitely crawl, walk, run. Don't jump in with a really complicated part with fancy things, and reach out to your support provider. Hopefully that's PADT, and we can help you figure it out. But these are pretty powerful tools, and I really recommend people check them out. Any parting shots? Did I forget anything else? I think we covered them all.
Yeah, I think I've blundered my way through enough. But no,
cool stuff.
There's always a lot, and again, I mean, this is more of like these conversations are weird because it's like an update presentation, but we're hitting some what might be enough highlights on what actually happens, and so there's a lot more that like we're not talking about. So
right.
That's kind of been my comment of like, especially in the topology optimization, is people looked at it maybe 6 or 7 years ago, and then it's like, oh well, it didn't do this. It's like, just look at it again, like, and especially if you depending on your license level, this is included. So so it's you don't have to bring in another tool. This is something that you have in house and can do.
Okay. Yeah, it's so true. I'm excited. I think the other thing that I have to keep reminding myself on these tools is, when we talk about mechanical or fluent, we're talking about 20, 30-year-old codes that are being refined and new features added. But these are kind of from the ground up, relatively new tools or new adaptations of mechanical or space claim. And there's a lot more there than we can cover in the podcast or in a webinar. So definitely check it out. Don't assume it's missing.
Yeah. And I mean, there's all sorts of, kind of validation studies in the documentation. So if you just, there's always skeptics that are just, going to say that, we're just making stuff up. Like there's been a lot of work to make sure that it's not just a random number generator. Like there's a good foundation in real life for this.
Very, very true. I hear that. Well, as always, Doug, I want to thank you very much. I hope you have a good 3-day weekend. We're recording this right before the 3-day break. So enjoy the heat before the cold comes.
The heat, then the snow. Hopefully the tomatoes survive.
Ours all boiled up.
Yeah, I might be taking Tuesday off as like bereavement for the garden that used to be.
Take pictures now. Before it's too late. Yes. All right. Well, enjoy. Always a pleasure. And we will talk to you soon. Thanks. After talking to him, I decided that I really need to find a way to maybe have PADT hire me as a contract engineer so I can do 6 months or so of real simulation for just kind of get deep into these tools. I really want to play with them. Really frustrating not being able to. I hope you got the impression that these are real value added capable tools and not just something, we used to sit around and talk about being able to do these things someday, right? Someday we'll be able to do this. Someday we'll be able to do that. Well, we can do them now. It's pretty cool. So to learn more, you can check out Doug's webinar on brighttalk.com. I searched for PADT space additive space R2 and it came right up. Or you can just search for PADT and find it in our list of webinars. But do check that out there. And as always, reach out if you have any questions about this topic or any others. So it's time for our commercial. And for today's commercial, let's talk about additive and how PADT is uniquely positioned to help. As you may or may not know, we have 3 verticals at PADT: simulation, design, and additive manufacturing, or 3D printing. And many companies are at a crossroads where they're trying to bring all these 3 things together to take their products to the next level, to get that extra added capability or functionality or life. And where it is true that many consulting companies can help explore 1 or maybe 2 of those aspects, PADT is one of the only firms, and really the only one that I know of in the world, that can address all 3. We can talk about all 3 of these and how they work together. So why not reach out and let us help bring 26 years of experience to bear on your initiatives. So shoot an email to info@padtinc.com and let's talk about it. Let's set up a call, see what you're trying to do, and see how we can help. We're doing it with other customers. We'd love to do it with you. And you don't have to be local. We can do that around the world. All right. Ansys stock, not much to talk about there. Definitely the market took a downturn this week, an adjustment, I guess they call it. Ansys peaked a couple weeks ago at 354.87 a share, and it's down to 321.21 a share right now, right before Labor Day. But if you plot it next to the S&P 500, you can see that it just pretty much went down with the market. That's a pretty straight fall. Nice peak, nice fall. It's a nice looking graph if you don't have money invested, or maybe it's time to buy. I'm horrible at investing, so I don't know, but still very strong. The stock is still doing very, very well, even with that adjustment. There's only one bit of Ansys news to share. They actually won a Gold Stevie Award for being a great employer. You may recall that PADT won for our tech support group a few years ago, and it's a pretty prestigious award, and we're really excited to see that Ansys won one for being how they employ their people, how they care of their people, and knowing many of their employees very, very well and friends with many of them, I can say that it's a well-earned award. So congratulations to everybody that made that happen. We don't have any announcements at PADT, nothing new going on with us, just same old, same old. Ansys blog-wise, I picked two articles I thought were interesting. One is called The Top 3 New HFSS Features for 5G Antenna Design. Well, even if you're not a 5G antenna designer, I found it very interesting because 5G is everywhere. Everybody's talking about it. It's a really nice look at how they use simulation to make better antennas. The second is something near and dear to my heart, which is using electrification for sustainability. And basically, it's an article about how the benefits of electrification are in big demand. It's not just something that people are looking at, maybe doing someday, but it's definitely a thing now. And simulation, of course, enables that electrification, as we're seeing over and over again. Events. So we've got one webinar on the calendar right now. I think we got another one coming up a little bit in October, but the second one for September is Twin Builder Updates in Ansys 2020 R2. And I recommend this for everybody because everybody should be, I don't know if you're a CFD guy or a structural person or you do electromagnetics, we're all talking about taking our models and putting them into a system level model. And that's what Twin Builder is. It's the system level modeler for Ansys. Really need to check this out to see what's new. It's growing. It's becoming more capable. It's becoming more powerful. And that's going to be on the 16th at 11 o'clock Phoenix time, Pacific time as well. You can, as always, sign up on brighttalk.com or go to padtinc.com/ and then go to events page and you can see the sign up there. You can click on the link and sign up there. You don't have to listen to it live, but do register so you get a reminder when it's been recorded. So we got a lot of events going on, which is what I said. So I didn't write them down. I'm going to go to our webpage, padtinc.com/events, and take a look at what's there. And there's a lot. First off, for those of you that are local, we're hosting the 6th edition of our COVID-19 response to not being able to socialize called the Arizona Tech Business Networking Event. This is on Zoom. We get together from 5 to 6:30 every 2 to 3 weeks, and we just talk and network. We go into small rooms and we meet each other, and it's a lot of fun. I kept on thinking that, well, one of these days nobody's going to show up, but we keep on getting more people. So very popular. And then in the middle of the month, we've got a 4-day event, which is basically our 3D printing user group meeting. So if you are involved in 3D printing at all, I recommend you check it out. We've got 4 days of events and in general, 1 or 2 talks each day. So we start the afternoon with a customer talk. This is not a sales conference. So the customers are going to talk about what they're doing. And then we're going to do a panel with experts on the topics. So the first day is on the 14th, and that's a discussion from a customer on 3D printing injection molded inserts, and followed by a panel on how to manage an additive production line. So people are setting up shops to make parts with additive manufacturing. How do you do that? Then the next day, a really great customer is going to talk about how they use 3D printing for construction and how they make basically models of buildings very useful and fun. And then we're going to talk about functional prototyping. So the focus there is making prototypes and how to make functional prototypes that you can use to drive your design faster. Third day is really looking at design. And we've got a discussion on the use of additive manufacturing for product development at Otter products. So you may have an Otter box or another Otter cover for your iPhone or your Android phone. They're Ansys users, and they're going to talk about how they use Ansys to help drive their product development for their consumer product. And then the final day is focused on medical. And the first talk is a customer that's using 3D printing for pharmaceutical equipment. And then we're going to have a discussion talking about how people used 3D printing to fight back COVID, kind of like our discussion here about how we used Ansys to do the same thing. So that's our PADT Virtual Additive Manufacturing Conference, or PVAMC. We'd definitely love to have some of our listeners attend that. It's open to anybody, anywhere in the world. So in the middle of all that, we've got some other events. It's AZ Bio Week, or AZ Bioscience Week in Arizona from, I think it's that same week, the 14th through the 17th. We're big participants in that, and we'll be running around doing virtual events for that as well. I'll be at the White Hat Life Science Investors Conference, which runs the afternoon of the 15th and all day on the 16th. And this is basically a startup-oriented pitch competition and speaking about startups in the medical space. I'm very excited about that one. It's a popular. I love that event. Every other year we do it here, and then on the other years, on the odd years, we do it in Colorado. So it's a great event. We've also got the webinar I spoke about with Matt on the 16th, and then the AZ Bio Awards are that night of the 16th, which is going to be, because we can't do it live, we're going to do it as a television show. So one of the local TV stations is actually going to do an hour-long show about the winners. And then PADT is sponsoring, and I am basically introducing a really important event that's near and dear to my heart that we've been trying to put together for some time, and I'm very excited about it. So it's through the Arizona Technology Council, and it's called the Tech Inclusion Forum. And it's the first of hopefully many events. And we're going to talk about understanding racism from a historical context and a call to action on how tech companies can make a difference in chipping away at systematic racism, institutional racism. So that's going to be on the 23rd from 3:30 to 5, and it's virtual. And it is an Arizona Technology Council event, but everybody is welcome that wants to participate in the discussion, because the problem is everywhere. And then we're doing a very similar event that we'll be sponsoring, called STEM Education and Workforce Equity Forum. And that's brought by a group in Colorado called STEM Generation, which we're active in. And they basically educate kids for STEM. They help teachers and families do STEM education. And so it's a pretty exciting event. We got two basically inclusion and equity type events coming up, one right after the other. And then finishing up the month, a very busy month, we will have a booth at the Colorado Life Science Innovation Forum and Trade Show. Day 1 is on the 30th, and day 2 is on the 1st of October. And like I said, we're gonna have a booth there, and we're very excited to see the people presenting and the talks and things. And that what they're doing for that one is it's going to be in the morning on the first day and the afternoon on the second day. So they're splitting it up. So if you do attend, if you're from Colorado or attending this Colorado event, please stop by our virtual booth. We will be there and would love to talk to you and just say hi. And then we've got other stuff in October and November that I'll talk about in the next podcast, but that pretty much covers a lot going on in September. So we packed a lot in there. That's it for events for PADT. Just want to thank everybody for listening to our podcast and for making it such a fun thing to do. Don't forget to subscribe at www.padtinc.com/opt-in. That's for our newsletter. And you can subscribe to the podcast wherever podcasts are subscribable. Do spread the word, let other people know about it, and don't hesitate to reach out. I thank you very much for listening, and we'll see you soon. Thank you for joining us for the All Things Ansys podcast, episode 71. As a reminder, this podcast is not affiliated in any way with Ansys Inc., and the opinions expressed are those of the people on the show only and not of their current or former employers. For more information, please visit www.padtinc.com/blog, and please share your thoughts and questions through an email to podcast@padtinc.com. See you next time.